I have put up in front of you welcoming slide for the tutorial. So we have set up a deployment of Dask on Binder. If you go to this URL, you'll have to type it in, I'm afraid. Then at that location, which is here, you'll see the big Launch Binder button. If you click on that, then after a certain amount of waiting, you will get a screen that looks something like what you see in front of you. You can be doing this while I start and explain what's in this tutorial and what we'll be doing and a little bit about Dask in general. I'd also like to introduce Jim. Jim also works at Anaconda on Dask with me, and he'll be handling the second half of this tutorial, and I'll be doing the first half. Also, I'm told that the Wi-Fi is not the fastest, so please bear with the system. It might take a little while for things to come up for you. Did anybody not get this URL? Are people still typing it in? I can leave it there for a few moments longer. Okay. So welcome to Dask. How many people here have actually used Dask before? I see a smattering of hands go up. So we will start at the beginning and take you through what Dask is and why you might consider using it. And hopefully at the end of this short hour-and-a-half period, you'll at least be interested enough to go off and try things for yourself. Dask is a pure Python parallel execution engine. So it's a way that you can take the normal Python-based data analyses that you might already have and scale them out, both on just a single machine, scale out in the amount of memory that you can use and using all of the cores on your machine. And as you'll see in the tutorial itself, scaling it to a cluster in the cloud on your company's deployment or wherever it may be. It's all pure Python. It's all pretty approachable. And the whole point of Dask is to reuse all of the Python tools that you're familiar with so that you don't have to learn new stuff. People still typing? Can you put your hands up if some of you have already managed to get to an interface like this? See, that's not bad. Okay. Okay, so that's to be expected. If you go to the documentation at this address, or just search for Dask, then there are examples there. There's API reference. There's a full set of everything that you might need, including more tutorials. So at the end of this tutorial, if you find that you want more, then that's the place to start. Now, on the left-hand pane here, there is a file selector. This might have come up immediately for you when your interface starts. We will be starting with number 1. If you double-click on this, then it will open in one of these tabs, like this. And you can click on the icon here to get rid of the selector, just so you have more space on your screen for seeing what you're doing. The right-hand panes here will only come up when we're using a Dask cluster shortly, so I'll show you what those are about in a moment. Okay, so the first of the 2 notebooks is to do with data frames. If you don't already use Pandas, then this might seem a little strange to you. I'm assuming that most of you know what Pandas is. Anybody not know what Pandas is? Okay. Anybody too shy to admit that they don't know what Pandas is? Okay, so that'll make this, it'll make a bit more sense if you already use Pandas. So, Dask, one of the things that it can do for you is scale out your existing Pandas workflow. It does this by having an API which matches the Pandas API and implements most of the things that you might do with a Pandas data frame. So, for example, I'm going to go through a short example here in which we're actually going to use Pandas directly. This is using some data in CSV format that happens to be on Google Cloud Storage. So in a particular public bucket, is the font's okay, by the way, yeah? Everybody can see that? Okay. In a particular bucket that's publicly available, there are a bunch of CSV files. This is taxi trip data over a particular year, and there are a few of these files. Each of the files is rather large, and this is the kind of work that if you're using Pandas, you would be used to. You can open one of these files, and you can read the first 1 million rows in this case. So this is just running in a single thread in a single container in this case. It takes a little while. This is basically waiting for download to happen from the cloud to the client, and then to be passed into a data frame. Having done that, we have a data frame. Now you see the slowness of the Wi-Fi. So it obviously takes no time to display a data frame, but it does take some time for all of these values to actually be rendered within the browser if the Wi-Fi is slow. So we have a load of stuff here, a number of columns, and a lot of rows. But this is still only a small subset of the complete data frame, and we can do some normal Pandas-like things to it. So one of the fields available is passenger count. We can add up in these 1 million trips, how many passengers were there in total? And it was this number. So there was 1.68 million passengers. Okay, that makes sense. We can also do some more complex things, such as what's the typical, or strictly speaking, the mean trip distance for those rides that happen to have one passenger exactly, and that is 2.9 miles, at a guess, not sure. And group by, so these are the kinds of things that people who use Pandas do all the time. It's roughly equivalent to doing similar kinds of operations in SQL. Okay, now we get to a little bit of magic. So by executing this particular cell, after the Wi-Fi does its thing, we will have a nice little widget appear here that is an interface to a Dask cluster running within this infrastructure. Wait a moment. This will eventually work for everybody. So there we are. We have a cluster, and it has 20 workers. Each of those workers has 2 cores, and the total amount of memory available is 140 gigabytes. Now, that's quite a lot of memory. The interesting thing here is how easy it was to get this up and running. So that's a lot of processing power. We next make a client to the cluster, and that client is the thing that's going to talk between the Jupyter kernel that's running here on a particular pod with the rest of the cluster. You also see that these panels on the right-hand side are populated with some stuff if it's rather empty just for the time being. So, lots of times, if you want to do distributed data frame work on a cluster, you will do exactly the same thing as you did for Pandas, except replace Pandas data frame commands with Dask data frame commands. So Dask data frame.readCSV looks a lot like the one that we had before for readCSV, except that we simply give it this URL, and Dask knows how to interpret this as being on Google. Some parsing commands, these are the same kinds of things that you would give to Pandas readCSV. One interesting thing is that you have this wildcard character. Dask will expand this to load all of the files in one go. So when I call this, this has a .persist here, which means that the cluster will start straight away, loading this data and storing it in memory. And you can see some exciting things starting to happen on the right-hand side of the screen. At the bottom, we have basically a progress bar with 3 items here. We have the read block, which is get me some bytes. We have the read text, which is pass these bytes into Pandas data frames, and they're going to be apparently 365 pieces of this. And then from delayed is look at these blocks of data frame and consider them as being one giant data frame across the whole of our cluster. You see this is working, data is being loaded, the time is dominated by getting these blocks, so you can see the difference. You have these, this is a time graph here for all of the 40 cores that we have working. These darker pieces correspond to waiting for bytes to download from Google, and these slightly lighter green blocks are taking those and turning them into Pandas data frames. The important thing to realize here is that it's actually Pandas that's doing the work. And Dask is acting as an orchestration engine to farm out this work across the cluster and to call Pandas on the pieces that we're going to marshal. This may take a while. Again, there's the Wi-Fi is what the bottleneck is updating this. It should only take a few minutes for the whole thing to complete. If you're executing cells along with me, then hopefully this is running for you too. Put your hands up, please, if you have successfully started a cluster. See a number of hands, but not everybody. And of those people, how many actually have this running? Okay, more or less the same people, a few not. Okay, so it will take some time for all of this to start up. Part of the time is down to Google allotting resources. So we have to wait for all of those to come online. Part of the time is just waiting for the Wi-Fi to catch up. So please bear with me. I will continue on. The cluster will remain live at the end of this tutorial for a while so that you can run through this in your own time as well. Okay, so we have this thing that we have called df. It is a data frame. It just happens to be split into many pieces across the cluster, and we can do data frame-like things to it. When we do, then it will operate on the pieces of of Pandas data frame that are scattered across the cluster. So when we do this, oh, actually nothing happened immediately, and this takes us into a slight detour, which is Dask is lazy by default. That is, it will not do work until you explicitly ask it to do work. The way that you ask it to do work normally is this .compute method. So we have this thing, and it is a Dask scaler. So Dask already knows that this thing will output a single number. In order to actually get the value of this and to start things happening on our cluster, we're going to have to call this compute method on it. So for the first one of these, where passenger count.sum, we already saw this before for the subset, I will actually type this in for you to show what happens. Or copy and paste, which is more convenient. And now we have a value. You saw, again, a load of things happened on the right-hand side. I'll show you what that is in a moment. But we have here 245 million passengers. And there's only about one passenger and a bit per ride. So that actually roughly reflects the total number of rows in this data set. That's quite a lot of data. It's not massively big data, but it's more than you would conveniently handle on a single machine. Now, what happened on the right-hand side? We have some yellow blocks. If I zoom into this block, it's called getLength. So Dask did some analysis of the lengths of each of our data frames. It also called sum on each of the pieces of our data frames. Now you have a lot of sums and a lot of counts. And this red bit, when red shows up, it means that communication is going on. So all of those pieces of length and pieces of sum have been brought to the same worker so that they could be added together to make a total length and a total count. And that's how you get the total sum at the output here. It would also be the kind of thing that you did for the average. And I will give you some minutes to try the next two little requests here. This will hopefully give some time for the people waiting on Wi-Fi and Google to catch up. In the meantime, you can put your hand up to ask general questions about why am I here, what are we doing at all, and I'll try and answer them. Also, Jim is moving around at the back, and maybe some of the people can help with individual issues if for some reason your particular interface is not working. You have a question? Start with the easy questions, yes. So the question was, what is the difference between Dask and PySpark? PySpark also has a data frame abstraction, API, which enables you to do things like this. A big part of the difference is the implementation. So PySpark is built on Java. Whenever you do something on the Python end, it's translating those into Java commands that are sent off to Java workers. If you combine that with a Python function, then that function runs on Python workers, which take the Java data frame and deserialize it to Python and do something and then serialize it back again. That can be unpleasant in some cases. If what you're doing fits very well into SQL style, pure SQL, then Spark will likely do a pretty good job of it, and it's a fine solution for what you're doing. However, the data frame abstraction is just one of the things that that Dask does for you. There's a lot more that Dask can do for you, and we'll get into that particularly in the second half of this tutorial. If you're already using explicitly Pandas and Python and you like Python, then it's also nice to use a framework which is all Python, and the backend that's executing the commands is really Pandas. So there is no translation layer here. It's just marshalling of which pieces get executed by Pandas on which worker. So the scaling out should be smoother for that reason. But if you already have working PySpark workflow and pipelines, then I'm not going to say that you were foolish to use it. It obviously has a pretty good name for a reason. There was a question up there? The question was, how mature is Dask compared to other parallelization regimes, and what would auditors think about it? I can't tell you what auditors would think, because I'm not one, and it would depend on them. Different companies and institutes will have their own policies regarding what they think is allowed and what isn't. Dask has been around now for a few years and is used in production at certain locations that I won't go into. So it's certainly good enough for some. In the Python data ecosystem in general, many open source projects are listed as alpha or beta, but are actually used in production every day, and that includes Dask. So if you use Pandas, and Pandas is not at version 1 and calls itself beta, then it's in the same category, I would say. Some parallelism frameworks have been around for an extremely long time, like MPI, IPyParallel is, 10 years old or something like that. And they work fine and they're well established. Whether you would call them production level at the highest security and monitoring guarantees, I don't know if that's true for any of these, actually. So this is the reason that some, let's say, defense-oriented institutes want to really control everything about their clusters. On the other hand, Dask makes it really simple to set up Scratch clusters for investigation. Things spin up quickly. You can do interactive work in an isolated piece of your cluster very easily. Could you expand on that? Okay, so the question is how performant is Dask versus getting a machine that can fit all of your data? Is that, yeah. If you can fit all of your data into a single pandas data frame and call pandas functions on it, then that will likely be good enough for you. Pandas is fast, it's well optimized. You can get the use of multiple cores using Dask, but Dask always, any system like this always comes with overhead as well. Exactly how well Dask will perform versus Pandas will depend on what it is that you're doing. But Dask handles data that's bigger than memory, and it handles data across a cluster. So for example, in this data set, most of the time is spent waiting for data to appear from the storage backend. If you have a single network card, that could be a problem. So try it, is usually what it comes down to. And we'll have just a final question, so we should move on after. There is a centralized scheduler that farms out work for the workers, and the workers are Python processes that listen to that scheduler and do work. So in that sense, yes, there is a common way for these things to be architected. Everything's a Python process, though, which will be nice for those that really like Python, which is most of us at a conference like this. And you can look at the code and figure out how it actually does what it does pretty easily. The graphs that describe what is to be done are dictionary-like things. You can view them as dictionaries if you want to. The communication happens over Tornado. There is a single scheduler. If your scheduler goes down, then you will lose your cluster, yes. There is some talk about how to get around that. Workers can come and go. Okay, so moving on. I will do the second of these. How many people have caught up? How many people are still waiting for things to happen? A handful. Okay, well, I will blame it on Google and I will blame it on the Wi-Fi, but I assume that you will get some workers and you will get some connectivity eventually, unless there's just too many of us in the room hitting the Wi-Fi at once. Luckily, I still seem to be live here. Average trip distance grouped by passenger counts. We had exactly the same thing above. So actually, I should just, I can copy it wherever it was. So the point is that the API is exactly the same as in Pandas, except that I do .compute to actually get an answer out of this. And you notice how quickly that happened. Actually, I got the answer before the indication appeared that the cluster was doing work, which is nice. But it was under a second. You can do real interactive data analysis now. Of course, all of the data is held in memory. So this is the next section. If I restart my cluster, eventually these things disappear, and I do this again. Okay. If I'm to do exactly the same computation as before, this now is going to take a while. The reason it takes a while is because it has to load all of the data. If I were to do each of these next computations, and again, I will just do the second of these once the first one is completed, you will notice that it has to load all of the data each time, which is fine if you can't fit all of your data into memory. But if you want fast processing for a lot of data being pulled from a remote source, if you can fit it in memory, you will want to fit it in memory, and deciding at what point to persist your data into memory of your cluster will have a very large impact on the performance of all of the operations that you want to do. So there's my sum. This is the same number as before, and all of the data have been processed, and this thing has been forgotten again. Now, I will get a different view of this and put this here. If I execute this again, then we will see a graphical view of the task graph being completed, where you see the green ones are waiting, so they've not been scheduled yet. The red ones are being temporarily held in memory while they're being processed. We're doing a group by here, so we're looking for each of these and doing mini group bys and then aggregating them and then doing aggregations on the aggregations. You can see this is a fairly complicated thing, but the point is that a lot of these turn blue, which is that particular piece of data has been processed, and as soon as it's processed, it's released from memory so that you don't use up your cluster's memory. This is very useful if you have more data than you have memory. It is what you will want to do. But in other cases where you care more about performance than you do about memory use, you will do the persist, which is this thing. So this is what we started off doing initially, and now I'm just going to run it again. This is basically loading all of your data into memory and keeping hold of it so that then anything that you do to it after that point will be fast. Moving on a little into, I already said some of this stuff, but in a bit more detail while that loads. A Dask data frame is a collection of Pandas data frames. Each piece is a reference to a different part of the original data set, in this case, some part of a CSV file somewhere. And you have an index. Exactly what that index is another thing to bear in mind when you want to optimize for performance. If you have an index that makes sense for your data, for example, if you have a time series data set, which we actually do in this case, every one of these rows has an associated date time. If you order your data on that column and you find the start and end of each of the pieces, this is known in Dask terminology as the divisions, then it becomes much quicker to do things with that index. So for example, if you want to do time-based, if you want to get a particular piece of data from a particular time, that's obviously much faster if you know which of these pieces to go to. If you want to do rolling aggregation, if you want to do resampling, if you want to do group by on month or something like that, then all of those things will become much, much faster if you nominate the time series column as being your index. So for the time being, when we've just loaded it, we have this index thing that shows up when we display the data frame just as ... By the way, this is showing you that Dask, the client here, doesn't hold this data in memory. It just holds a description of what the data frame is like. So we know what the column names are, we know what the column types are, but we don't see any data unless we do .head here to get the first few rows. This thing is our Dask data frame. And one of the most common things that you might do with a Dask data frame is map partitions. This basically runs a particular function on each of the pieces. So if I do that, then you will see confirmation that each of the pieces is a Pandas data frame, as promised. And there's quite a few of them. Now I will set the index. So you're used to setting the index in Pandas. In Dask, this has special meaning. We're going to do some shuffling and sorting of the data because the original data was not already ordered. And we're going to find out the start and stop of each of the parts that it's made of. You can see this requires a certain amount of work. You can see this dense layer here. This is a many-to-many shuffle layer. And if you look at the stream version of this, okay, update is slow. I'll wait for this to finish though. You can see the things that appear down here are called split, group, and join. So that is how you find out for each of the data frame pieces which of the final data frame pieces will it end up in. You split them into those pieces, then you shuffle those bits around and reassemble them. And that gets me my new data frame, so I think this is about done. The display is taking a little while to catch up. And now I have a data frame where you see the left-hand column, the index column, has been filled in with time values. So these are actual datetime-like things that we can do datetime-like things to. If we look at the first few rows, again, wait for the display, then we will see that this is 2015 data. And we start the very first row, apparently somebody took a trip right on the stroke of New Year. Actually, a few people did, which is interesting. And indeed, this whole thing has been sorted. If we look at the tail, then we get at the very end of the year. So people, it turns out, take taxis immediately before New Year's and immediately after New Year's. And the divisions look like datetime things. Now, the point of doing this, let's shrink this. The point of doing this is that now we can fetch a particular piece of data very quickly. If we want all of the rides on a particular day, .compute will take all of the rows that match this location and bring them into the clients for further processing. That looks like that. We have, this is now a pandas data frame with which I can do normal pandas things, and there were apparently this many, over 400,000 rows on that particular day. Or if we want to do explicitly time series-like things to it, for example, resample by hour, then we can do that too. And these things become a lot faster after you've done the setting of the index to a datetime column. This is just a taster, a feeling for all of the things that you can do with data frames in Dask. I hope you find that it works more or less like Pandas does. Everything feels natural. Not the complete Pandas API has been implemented, but a very good fraction of it has. Now it's downloading the image of this plot, so that might take a little while. Although, actually, I don't think I executed this. So I'll do that again. And now it should actually appear. Okay. So this is throughout the whole year, but resampled to 1 hour frequency, the average number of rides, and you can see some very clear variability there. That it's probably weekends, I think. This is a matplotlib output, not bokeh, so I can't zoom in on it for you. I'll also close this because it's just too slow. That should make the Wi-Fi slightly better for everybody else. Okay, so we've got to the end of the first of our notebooks. There are a couple of things for you to try, and we'll spend, let's see, maybe 10 minutes for you to catch up, try these things, and we'll have some question time again now. Good. Is there a way to process unstructured data using Dask? The answer is yes. There is both the delayed mechanism that you will see for the second half of this tutorial, and there's also another collection called Dask Bag, which works a lot like tools and iter tools, if you've used those things before. That is, you have list or dict-like things, and you're going to iterate over these and do usual Python-like things to them. So if you're used to that functional way of programming, then the Dask Bag interface is the one that implements that. The remaining interface that people might be interested in is the ND array interface, which does the same thing that the data frames thing does to pandas, the array interface does to NumPy. So you can have a single logical Dask array that is actually a pointer to lots of NumPy arrays that are either in files somewhere or are stored in a memory across your cluster. Yeah, go ahead. Sorry, a few of the methods are special in that it's implicitly going to get you in-memory data. So .head will straight away get you a small pandas data frame without the compute. There is some, but let me get it back again. Okay, maybe that wasn't a good idea because this will take a while to appear. Okay, I'll cancel that. The short answer is that yes, there is some documentation and there is actually more webinar-style introduction to what you might do with that. If you go under Dask doc pages, there are links there to it. It's not as thorough as it might be. The various screens of the dashboard are relatively new and have been developed quite heavily over the last year or so. So there is room for improvement for sure, but there is a lot of information there to help you understand what's going on your cluster, both on the overview of total amount of memory, a view of all the tasks and where they go, the graphs being processed as you just saw, but also at the worker level. So you can go to the individual workers and figure out what they're doing on a pretty detailed level.
You mentioned that you can load the data into memory. What's the benefit of using that?
It's into the memory of your cluster. So it is possible to get a single machine with equivalent amount of memory. You could do that. But if you were doing that, then you probably still would want at least multi-core processing of that data. And you could do that with Dask. So using Dask to compute an in-memory thing on a single machine with lots of cores will be roughly equivalent to doing the same thing on a number of machines across a cluster. On a cluster, communication from one machine to another will be somewhat slower than from one process to another on a single machine. On the other hand, you typically get a lot more network bandwidth out of it. Setting up clusters of many small machines or small pods in the Kubernetes sense is usually preferred from a system administrator's point of view. So they will often already have systems for doing this, and asking for a single machine with 100 terabytes of RAM is probably not allowed, whereas asking for 100 terabytes of RAM in lots of virtual machines is. So it may be a preference and policy thing. Okay, we're about halfway then. I will hand over to Jim for the remainder. For those of you that are making good progress, which might not be so likely given the Wi-Fi, there is a third notebook which gives you, again, just a teaser of machine learning and Dask. If you are ahead of us, then feel free to go on to that. But we will move to the second notebook. I'll load it up. When we do that, please, if you have something running, execute this cluster.close at the end. This is to make sure that you free up the resources of your workers so that other people can use them. You can also, and probably should, shut down your notebook. So there is a tab on the left here. The little running person tells you what's running. So you can click shut down there. And then to open, go back to the files and double-click on delayed, and this will bring up the new tab. So I will bring you back your... Okay, ready to go? Go on ahead.
All right. Couple things real quick. How many people have not been able to access the Jupyter lab setup here? Show of hands. Are you able to get on it and you just find that you're sitting in a cell and it's just spinning, nothing's running? That's accurate? Okay, so that apparently is due to a proxy that you might have set up on your machine. Say that you are using Capital One's proxy. It doesn't like this setup. We found that that works for, we have another deployment on examples.dask.org. This uses HTTPS. This thing we're running on here right now doesn't, and the proxy doesn't like that. So you could either find a way to disable this because you're going through, say, not Capital One's Wi-Fi, but the guest Wi-Fi, and then you might get things working. Otherwise, you can go to examples.dask.org. You will not be able to run these same things here, but at least there's a couple things you might be able to play around with while we're talking. Yeah. Anyway, I'm going to be talking about Dask delayed. So this is another interface we use in Dask. So Martin was showing using Dask data frame, which looks a lot like Pandas data frames, but some workloads, people were talking about custom or non-structured data, don't fit within a Pandas data frame modality. There's a nice blog post done by someone about using Dask to do credit modeling. So this is, a highly non-structured process. We have lots of different steps going through. This was the graph that they generated. Lots of different workflows going through, moving data around. But this was all done with Dask. And this code looked fairly normal for Python. It's a lot of loops, a lot of functions. But with Dask delayed, you're able to parallelize this and scale this out across a cluster or a large single machine. So we're going to be talking about Dask delayed. So if everyone can open the delayed notebook and make sure that you have shut down the other notebooks. Cool.
Is this the same delayed notebook that's on the examples?
No, so the question was, is this the same delayed notebook that's on examples.dask.org if you're not able to get things running in this binder setup? It is not. There is a delayed notebook. It'll walk through some of the same information though. And you can follow along. These notebooks also can be run locally. So if you wanted to download it and run it locally, this one doesn't require scaling across a cluster as much. Okay, so first we're going to define a couple functions, adding in a little sleep to make it take some time. We have a function called inc, which is going to increment a number, and we have a function called add, which is going to add two numbers together. If we run this cell here, so we're going to increment 1, call it x, increment 2, call it y, add those two together, call it z. It takes 3 seconds. That's because each of these functions sleeps for 1 second. If we were to instead parallelize it with Dask delayed, so import Dask, the Dask delayed, Dask.delayed is a function decorator. So if you're not familiar with decorators, decorators in Python look like this. So if you put an @ sign above it, this will call that on the function and then return the output and name it foo. This is the same as if you were to do the @ sign is just syntactic sugar for Python. Anyway, Dask delayed wraps functions and makes them delayed. So normally a function in Python runs immediately. This makes it run at a later time. So here we're going to wrap the call to inc in Dask delayed and the second call, and then again down here add. This looks similar to the code we have up here. We're just wrapping all the functions in delayed. And it runs pretty much instantaneously. This is because we haven't actually done anything yet. So before we were actually computing, it was calling the sleeps. Now it's just built up a graph behind the scenes. To actually compute, you call .compute. This is the same as you saw in the data frame notebook. And it's going to run, and it takes 2 seconds. Does anyone have an idea why that might be true? Say again? Yes, yeah. So what happened here? Z is a delayed object. We can look at the task graph for Z by calling the .visualize method. And we can see that, yeah, inc1 can be called here and inc2 can be called there, and then we can add them together. These two can be done in parallel because they don't depend on each other. And so as Dask is scheduling these, it can run them at the same time and speed up your workflow. If you weren't sleeping, say you're doing some complicated math task, those would be able to run in parallel and you'd get speed ups across your code while writing code that still looks like normal Python. See, in here I have some questions to consider. I'm just going to talk through this one. So what would happen if the inc and the add functions didn't include the sleep? Say they were doing something else. Would we still be able to get parallelism in a thread pool? Does anyone have an idea? So it depends. Python has this thing called the global interpreter lock. The global interpreter lock means that you can only do one Python thing at a time in a single process. But a lot of mathematical libraries in Python release the interpreter lock. So NumPy, for a lot of operations, releases the lock, and so you can parallelize NumPy code. But generic Python, say you're working with strings doing things, you might not be able to get actual parallelism. In this case, the sleep call releases the interpreter lock, and you can do multiple things at once. If people have used Numba before, show of hands, who has heard of Numba or used Numba? Excellent. So Numba is, for those that don't know, Numba is another library for speeding up Python. It compiles it down to a native code. You just decorate functions that look like normal Python and it'll run them faster. But one of the options you can add is a no-gil decorator. And so you can say, I want to compile my function with Numba and I want to release the gil or the global interpreter lock. And then that'll run in parallel. And so Numba and Dask play really well together when you're building up these custom workflows. You can get true parallelism by writing your fast code in Numba and then scheduling it with Dask to run in parallel. Anyway, moving on. We have an exercise here. We're going to parallelize a for loop. So we have some data. We're going to loop through the data. We're going to increment each result, or each number. We're going to save it in a results list, and then we're going to sum the results together. So if I do this, I have to define data first. It's going to take sequentially. So each of these calls to inc is going to happen sequentially. And so that's going to take, what, 8 seconds about? Yeah, 8 seconds on the money. You can see what the total is. So your job here is to parallelize this. You're going to put Dask delayed somewhere within this loop, maybe a couple spots. And you're going to find a way to parallelize this so that it doesn't run in 8 seconds, it runs faster. And we'll give you about 5 minutes or so to work that through. So the question is, can you explain why or what Dask is doing behind the scenes when it's scheduling these? So Dask has a couple different schedulers. So in this case, we're running with the default scheduler, which is threading. Uses the local threaded scheduler. There's the distributed scheduler, which is what you saw in the last notebook. We have one that uses multiprocessing that we don't recommend people use anymore. It's not as efficient as the distributed scheduler. The distributed scheduler is a bit of a misnomer. It runs perfectly fine in a local machine, and it's easy to start up. So we recommend either using the threading one or the distributed scheduler, depending on your workflow.
So if you were using the distributed scheduler, would you need to use statements?
So the distributed scheduler can have multiple process workers, and each may have a thread pool within. And you can say how many threads you want per worker and how many workers you want per cluster. And so you can have a balance between getting true parallelism because you're using multiple processes and efficiency of shared memory by using multiple threads. Usually we recommend a mix. No. Yes?
Is there a difference for CPU bound and IO bound operations here?
Yeah. So depending on what you're, can you explain again what you mean by that?
So ski or sleep doesn't require computation.
Mm-hmm.
It's positive to go. If you have a tense CPU computation pattern there, how would you know? Because then releasing guild is not too efficient. That's what's happening. Maybe.
Yeah. So because things are happening in threads, you have to deal with normal performance issues for threads. So are you going to have more threads than cores in your CPU? Are you going to be doing I/O bound work where you might want to over saturate a worker? I think it really depends on your workflow. The scheduler doesn't do anything in smart knowing if something is I/O bound or CPU bound. Show of hands, who has a solution to this exercise done already? Would anyone like more time? Like a minute or two more? Okay, we'll give you about a minute more. All right, we're going to move on. So there's a couple different ways you can actually parallelize this. Here is one example. So in this case, we have the same results list that we're saving. We wrap the call to increment in delayed to delay that call, and then we wrap the call to sum in delayed to delay that call. I'm going to run that. And if we were actually time that, that would take about a second. Yeah. Because we have 8 threads and we are computing 8 things in parallel. Did anyone not wrap sum in delayed? When you did it? Did the graph, here, let's see, what did I call this? So right now we have the result. This is our delayed, no, total. That's what I'm looking for. So here's the existing graph. If I visualize that, you can see it's running 8 different increment calls. All those can be done in parallel. And then we have a single sum call here. If I instead remove the wrapping of delayed around sum, so we're still delaying the increment calls, but not the call to sum, I can visualize that. And we get this nice fun tall graph. So what's happening here is that delayed objects implement a lot of Python's normal operators, so you can add them together. Like, here's total. I can do total plus 1. It'll give me a new delayed object. And then the sum function in Python just adds them together by using the addition operator, and so you get this nice big chain. This is way less efficient than actually wrapping it. But you can see that there's a couple different ways you can actually parallelize your code. This still runs in parallel. We just end up with a lot more tasks than we need to. All right. If you are running, in this example, on a binder, you can start a Kubernetes cluster here. We're going to be doing some stuff that will require distributed. Some of this might run fine if you're running locally, if you've had to download the notebooks due to Wi-Fi issues. So I'm going to spin up a quick cluster. Again, make sure that you have already shut down your previous cluster if you haven't already. Otherwise, you're not going to have resources. Cool. All right. And we'll connect. Cool. So we have another exercise here. We're going to be parallelizing a for loop with control flow. This time we're going to be running on a distributed scheduler, not on the local scheduler. We have a function called inc, a function called double, and a function called isEven, which says if the number is even. We're going to loop through the same data. If it's even, we're going to double it. If it's odd, we're going to increment it, and then we're going to take a sum of the total results. Your objective here, again, is to parallelize this code. So sequentially, we're looping through all the data and doing an operation each time. This should be parallelizable. You're going to want to wrap some of these functions in delayed, but not all of them. You have to figure out exactly where it makes sense to do that. And we'll give you about 3 minutes to do this. All right, let's walk through the solution here. So in this case, we don't delay the isEven call. We want to do that at runtime, but we will delay the calls to double and inc and sum. The reason we don't want to delay isEven is because, well, here, let's see what happens if we do it. So here we can compute, and we can take a look at what the graph looks like. So we each have one double inc every other number, and then we sum the results together. If we wrap isEven in delayed, we get a nice error. Truth of delayed objects is not supported. The reason is we don't know what the value is when we're building this graph. We don't know what x is exactly when it's being built. It could be even, it could be odd. We don't actually know what the result is at that time. We'd like to do that at build time, and we can't, if we delay it, we won't know. You can't compute. Sorry. Given a certain delayed object, say total, we don't know if it's true or not unless we compute it, is what I'm trying to say. Which is why you get this error. All right, our final example here, we're going to be walking through some data frame computations. So when we're using Dask data frame, Dask is building up these graphs behind the scene for you. When you're using Dask delayed, you're building up the graphs manually. You can do the same algorithms using Dask delayed, you just have to manually write them out. So we're going to be walking through one of the examples that you did in the data frame notebook, but building it out using Dask delayed and seeing what the functions you're composing are doing. So Parquet data in the cloud using GCS. We can load that with Pyro, which is a great library for reading various different file formats. It's going to take a second. So same data you were looking at before. And so we're going to be building up this computation that you could write using Dask data frame, using Dask delayed instead. So we want to figure out what the mean passenger count is for all of the files that match this glob. So we have a couple functions here. One that loads a file into a Pandas data frame. And then we can loop through and we can say, here, we're going to load our Pandas data frame. We're going to take the passenger count and we're going to compute its sum. We're going to take the passenger count column and we're going to figure out how many numbers there are in it. And we'll save both those results. And at the end, we will sum all the sums together, sum all the counts together, and then divide the sums by the counts to compute the mean. So this is what you would do, this is what Dask would do behind the scenes if you actually wrote out this code using Dask data frame, but instead you're composing together these functions. So I can run this sequentially, but it would be good to parallelize it because each of these files can be read in parallel and the mean of the sums and the counts can be computed in parallel, and then you can aggregate them together finally. So your job is to figure out where in this manually written serial code you want to add the delayed decorator to parallelize it. I'm going to give you about a minute or two to do that. All right, by a show of hands, how many people have a solution at this point? How many people would like a minute or two more time? No one? I guess we'll move on then. Cool. So, walking through this, what do I need to delay? So we defined a function up here. We loop through. Do I want to delay this function? Yes. Yeah, we do. I want to make sure that the file name or files are loaded at compute time, not at graph build time. What about this? Do I need to do anything here? No. So Dask delayed objects implement methods. So if you just have a delayed object, you can call what other method on you want. So here it's automatically using the list.count method just by calling it. All right. How about this? Do I need to do anything here? No, same thing. It'll automatically use the methods and the attributes on the delayed object, and at runtime they'll be used on the computed thing. Appending to sum. Same thing. It's fine. Same with counts. Do I need to delay the call to sum? Yep. And we'll also do it here. How about this? Yeah, I don't need to do anything with the division here. That will just automatically work. As I said before, Dask delayed objects implement a lot of the operators, and so that should just work. So if we run that, we get mean, which is a delayed object, and I can compute it, and that should run in parallel. And here we can see the big graph we've actually generated. Loading a file, doing some getting attributes, count operations, sum operations, and then finally aggregating things together. So for a bit of motivation, that's the last of our exercises, but we have a third notebook here, which I'm just going to walk through. This is doing a grid search with Dask delayed. So we have a library called DaskML, which does a lot of Scikit-Learn stuff using Dask. It'll parallelize things. It'll scale them out across a cluster. One of the things we implement there is a grid search. For people that aren't familiar, grid search is taking a bunch of different parameters and trying to figure out what of those parameters give the model that you're fitting the best score for some metric. That can all be done in parallel. That's fitting a bunch of different models and then comparing the results. Dask uses Dask delayed to build up these operations in parallel so that you can have your grid search operation scale across a cluster and complete a lot faster. I'm actually not going to run any of this. Never mind. But that's a library that exists. We found that Dask delayed is very useful for parallelizing existing code. So we've used it to add Dask to other libraries. Teapot, I think, was one that was added recently. Dask can now be used by Teapot optionally. DaskML parallelizes Scikit-Learn. What else uses it? Scikit-Image now uses Dask internally for some things to parallelize out. So it's a good way to take existing code you might have written and try to figure out a way that you can scale it. At this point, we have time for questions, if anyone has questions. No, she's...
I don't know how to. Oh, there we go. I was just wondering if you can query the status of a future Dask delayed thing to see if it's done or not, like whether it's waiting or being computed or done.
So the question is, how can you monitor computations as they're going through? So Dask delayed just builds up graphs behind the scene, the same as Dask data frame does or Dask array. Or the other collections that we have. The ways you can monitor them is through the dashboard. So here you can see our file name to data frame computation as it's moving through. This runs in real time. This is the best way that we have for you to see what's going on. There is no way to query the status on an object, but you can watch as your tasks progress through. Did that answer your question? Okay.
Anyone up here have questions? Just checking.
Anyone else? Oh.
Will it ever kill it and retry? Oh, I'm sorry.
Say again?
If the taskbar goes red and stays there for a while and just never comes back, would it kill it and retry?
So the red tasks in the task stream are data communication. Is that what you're asking about? Okay. So the general question, I guess, would be, will Dask ever retry computations if something goes wrong? So there's a couple answers to that. Say you have a function that you've written in Python or some low-level language that can cause seg faults, and that function is bad. Dask will run it if you parallelize it across, and if it kills the worker, like if the process seg faults, it'll try it again on another worker, and it has a certain limit before it says, no, I don't trust this anymore, I don't think this function is good, and then it'll just kill the whole process. It'll say, no, your code is bad to go fix this. But if there are periodic failures, say that you have a function that uses too much memory and the OS kills it, it might try it again on a different machine.
I saw in the documentation for Dask Kubernetes, you have this adapt function, and it seems like it can dynamically adjust the size of a cluster. Could you explain a little bit about how it makes those decisions on like when to scale up nodes?
Yeah, so we have a couple different deployment platforms. This one we're using is Kubernetes. We also have ones for deploying on Yarn. So if you have an existing Hadoop cluster, you can deploy Dask on that. We have one for deploying on traditional high-performance computing clusters using job queue type things. And all of these follow the same interface where you have an adapt method and a scale method. So let's go back. Let's see. Somewhere in here I have a cluster object. Yeah. So on the cluster object, we have a scale method where I can set exactly how many workers I have. This is just a nice GUI for doing the same thing. And then we have adaptive scaling where I can set a minimum and a maximum number of workers, and it'll scale your cluster smaller or bigger depending on the amount of work that's going on. That algorithm that we use to determine that, how many workers you might need, when you'd want to scale up, when you'd want to slow down ramping up, has changed a couple times, but it's based basically on the amount of memory that is being used by computations and the amount of CPUs that you're currently using. Or is your cluster flooded with too many tasks, and would adding additional workers help you parallelize things more? Or are there a lot of idle workers sitting around doing nothing and it wants to scale down? Anyone else? Okay, well, oh, sorry. I'm sorry, I didn't hear that.
Use the microphone.
Do you guys plan to expand support into deep learning libraries, like for instance, TensorFlow?
So we have a project called Dask TensorFlow, which I believe is now part of the overarching Dask ML thing. So that will spin up a distributed TensorFlow cluster on your workers. You can do some TensorFlow computations and spin it down. In general, things like that would be best influenced by people that have ideas for how they might want to do this. We found that things work well when there's an existing community of users that would like to parallelize things out, and they can say what they'd like to do, and we can help them figure out a way to do it. So if you're someone that uses distributed TensorFlow and you might be interested in figuring out a way to have Dask do that for you, generally working with people that are domain experts in the field they're working in, say machine learning, and someone from the Dask organization that knows how to parallelize it, we can get a nice library worked up. But there's existing some support for TensorFlow. There's XGBoost, which is not deep learning but another machine learning. Same thing, we can spin up an XGBoost cluster. And the Dask ML org has probably a couple different issues around other things. Yep.
And a question regarding if I have one big server, what way Cell can speed up the current code? If I have enough memory, and I have multiple cores, let's say 12 or whatever.
The question was, if you have one big server, how would you use Dask on it? Yep. Yeah. So in that case, I'm going to kill this. Just to free up resources. So the client object right here, if I just call cluster, or if I can spell, that'll spin up a local cluster just on your machine. And so that's the recommended way for you running multiple processes on a single machine. And you can specify a number of threads and numbers of workers in that call, but that will spin up local clusters. So let's see what we have here.
That's when you use a different cluster, right? Or a different schedule.
No. So here we can see I have 16 workers running on 16 cores and about 64 gigabytes. That's just what's on this machine, the thing my Jupyter notebook is running on. This starts up a local distributed scheduler. So it's the same as if you're running across multiple machines, but it's just using processes on a single machine. Okay. Oh.
Oh, 1 second. Can you use the microphone? Thank you.
Is ML Dask up to date with the current Scikit-Learn implementations of the functions?
So DaskML doesn't try to imitate scikit-learn. We don't implement all of the algorithms. We implement ones where it makes sense. We have some things for doing model level parallelism, like grid search, and some things for doing data level parallelism. I don't know exactly what estimators are implemented at this point, but there are some that will mimic the scikit-learn API for doing fit and predict. It works with the latest scikit-learn, but we don't mimic the interface exactly, if that was your question.
Yeah, it was mostly about just, is it going to do the same? Will I get the same result? It'll just be faster? That's essentially my question.
Faster or works with larger data is the goal.
Okay, thanks.
Yep.
Hi, can I use Dask for parallel I/O? If I want to download a big file, can I parallelize?
Yeah, you could use that for, if you're just downloading files, there might be better tools for doing that, but it still would work. Okay, so we will be around all weekend if you're attending the rest of the conference, and please feel free to stop us, ask questions. Otherwise, we are always looking for contributors. If you would like to start helping out on Dask, if you are part of an existing community of users of some field and would like to figure out a way to use Dask to parallelize that, we'd be happy to talk to you. Thank you.
I just wanted to say that Jim is giving a talk about Skein, which is the Yarn integration method for Python, which is capable of deploying Dask on Yarn. If that's by Yarn, I mean Hadoop, if you don't know what that is. And I'll be giving a talk on intake, which is slightly related, more about how you get to your data, how you catalog what data sources you have.
Thank you.